Next, we're going to talk about experimental design. So to produce meaningful, unbiased results, experiments should be carefully designed and executed. So when I say unbiased, I mean I want my sample to be representative of my population. If it's not, then it's biased, right? So if I am looking to survey or sample adults in the United States, but my sample only includes college students, then that's bias, right? It's going to be leaning towards how college students feel, not all adults. So you need to make sure your survey is unbiased and that it is a representation of the whole population. And also that the people who are conducting it, their opinions are not coming into it as well, right? So when we're writing those survey questions, we're making sure we're really careful as well, or we're conducting an experiment that we're doing it as really systematically as possible, right? So we're not influencing decisions that shouldn't be influenced. Another thing we have to watch out for is compounding. So compounding variables occur when an experimenter cannot tell the difference between the effects of different factors on a variable. So for example, let's say to attract more customers, a coffee shop remodels using bright colors. However, at the same time, a mall opens nearby. Business at the shop increases. However, we can't tell if business increased because of the remodel or because the mall opened. So the two effects have been confounded, right? Another example. So let's say you're doing an experiment and you're doing something on weight loss, right? So maybe you have your clients exercise and change their diet. And what do you know? They lost weight, right? But you don't actually really know what happened. Was it more the exercise? Was it more the nutrition? Was it really both? So we've confounded our variables where now we really kind of can't distinguish what was the big factor there. So again, you want to really be careful and think about what else could be going on and influencing that experiment or even that survey. Another factor that can affect an experiment is the placebo effect. So we mentioned before that the control group usually would receive a placebo if we're testing usually medication or something like that. And the placebo would be a medication that has really nothing in it. It's usually a sugar pill. So it's completely inert. It doesn't have any drugs in it. However, the placebo effect occurs when subjects react favorably to a placebo when in fact, placebo has no effect. So this can happen, right? The human mind is an amazing thing. And sometimes if we believe that we are getting, let's say, the medication, so that maybe that person doesn't know, but they think they're getting that medication, they could really start to feel better. So that's called the placebo effect, where even though that pill is not having a physical effect on your body, you are actually feeling better. We can help to control that a bit, and that's with blinding. So blinding can help control or minimize this. And it's a technique where the subjects do not know if they are receiving the treatment or the placebo. So again, we've talked about that. We really don't want our subjects, in most cases, to know what they're receiving. Now, if I go back to my weight loss example, that's different, right? Obviously, the subjects know if they're exercising or if they're changing the nutrition. So there's some examples that's not going to work. But particularly for medication and things like that, we try to have it blind so a subject does not know if they're receiving the drug or not. Even better is a double-blind experiment, and that's the case where the subject doesn't know if they're receiving the drug, but also the experimenter doesn't know if they're receiving the drug. So if I'm the experimenter and I'm kind of distributing that medication, even I don't know who has the placebo and who has the real drug. Obviously, somebody knows, right? So there is someone in the background who's keeping track of who's getting what, but the person who's kind of conducting that research and giving medication doesn't know, so that even their own personal influences cannot affect the data, right? So they have no idea who's getting it and who's not. So even their own experiences, again, can't influence that. One challenge for experimenters is assigning subjects to groups so that the groups have similar characteristics. So if we have two groups, we do want them to be about the same, right? If we're trying to test a treatment. So when treatment and control groups are similar, experimenters can conclude that any difference between the groups is due to treatment, right? So we do want them to be similar so that we can see if there are differences. And to do this, we use randomization, and this is a really important thing in statistics. So randomization is a process of randomly assigning subjects to different treatment groups. Now, there's different ways to do randomization, so we'll talk about a whole bunch of different ways. In a completely randomized design, subjects are assigned to different treatment groups through random selection. So think of that like putting a name in a hat, right? So if I have 100 people who are going to be part of this experiment, I'm going to put 50 in one group, 50 in the other group. I'm just going to pick names out of a hat. All right, 50, here are you 50, here are you 50. Okay, so it's just kind of totally random. That doesn't always work for every experiment though. So in some experiments, it may be necessary to use blocks, which are groups of subjects with similar characteristics. And then a commonly used experimental design is a randomized block design. So what happens is the experimenter divides the subject with similar characteristics into blocks and then randomly assigns to treatment and control groups. So for instance, let's say I was testing a new drug or something in adults, like let's say middle-aged to older adults. So maybe I have 3 blocks. So I have ages 30 to 39, 40 to 49, and then 50 to 59, right? So these are my blocks. So I'm going to take my people in my experiment and I'm actually going to group them first. And then I'm going to randomly assign some to get treatment and some to be the control and not get the treatment. And I'm going to do this for each group. And same thing for this one. So treatment and control. So this part is still randomized. I'm still going to randomly select, okay, you go to treatment, you go to control. So maybe I put everyone who's 30, 39, put their names in like a hat, so to say, and kind of randomly pick them out. But I've grouped them first. So these are called your blocks. And again, sometimes it is necessary to do that to make sure that we're getting a diverse enough sample in both cases, right? I don't want to have one group be all my 30-year-olds and one group be all my 50-year-olds. That doesn't really help. So this allows us to make sure that the groups are a little bit more similar while still using randomization. Another type of experimental design, which is a similar idea, is called matched pair design. So that's when you pair up subjects according to similarity, and then you put one subject in the treatment group and one subject in the control group. It's sort of like the idea of twinning. So it's almost like you want to make twins. So if you have 100 people who are going to be part of your experiment, we'll say, I'm just using small numbers here, you would kind of find people who are similar, right? So maybe I would find someone, if I'm in the experiment, I would say, okay, I'm going to find someone who's similar to her, right? Maybe the same age or same weight, same geographic location or physical type, whatever you're trying to study. You're going to match people up so that you're kind of like making twins. And then one person goes to the treatment group and one person goes to the control group. And that kind of allows, again, your groups to be very similar. So you're trying to kind of create almost like matching groups. And that's called a matched pair design. And then finally, sample size. So sample size is just a definition. That's the number of subjects that we're studying. So if you're studying 100 people, then that's your sample size. If you're studying 1,000, then that's your sample size. And we'll talk more about sample size later because there actually are mathematical ways to calculate what your sample size should be so that you have a good enough study. The other thing we have to do is use replication and repetition, really. So replication is repetition of an experiment under the same or similar conditions. And this replication can occur in 2 different ways. So the first thing is that you need to make sure your sample size is large enough within the study. And like I said, for today, you don't have to worry too much about how do you know this. We're going to learn later on how do you find a good sample size. There are formulas we can use. So that's part of the repetition, right? So if you're doing an experiment, let's say we're trying out a new drug, and I only choose 10 people to be part of it, that's a very small sample. I'm only testing that drug 10 times. But if I choose 1,000 people to be part of it, I'm testing that drug 1,000 times. So I'm replicating that process more. So we want replication. We need to make sure that we are actually testing it on enough people. The second way that you can replicate, and it's not talked about as much in your text, is that you can have that the whole study is redone really by another team. So when we have good studies, good statistical studies, good data, what happens is it's peer reviewed, meaning we would publish our study and then others in our field, again, who are respected and have degrees and things like that in that particular field, would review the research and say, yes, this looks good. They did a good job. I can see they did their grouping correctly. They did their sampling correctly, their calculations. We agree, right? So this looks good. So that's peer reviewed. Ideally, there'd be another team who also redid the research, right? So they may take, do the same study with their own sample of people, and again, replicate that research to see if you get the same result, right? So we want to see, yes, in the second study that, yes, the drug is still showing that it works. So now we have two studies that were similarly done that both show the drug works, not just one. So replication can occur within one study, right, having a large enough sample size, but ideally it would also be replicated again at the end of the study. So if, or in peer, or at least peer reviewed by others in the field to see that it was done correctly. A lot of times research gets posted, by the way, and it's not peer reviewed. So you do want to be careful that you're not just saying, oh, it's a statistical study or a medical study, I'm going to jump on it and this must be true. You do want to make sure that it's published in a reputable journal. So there are some journals that are not reputable. There's others that are very highly respected. And then you want to make sure it was peer reviewed. So if no one else has looked at that research, then maybe be a little bit more cautious about the results. All right, a company wants to test the effectiveness of a new gum developed to help people quit smoking, identify potential problems in each experimental design, and how to improve it. So the first example, the company identifies 10 adults who are heavy smokers. 5 of the subjects are given the new gum, not Jim, and the other 5 are given a placebo. After 2 months, the subjects are evaluated and it is found that the 5 subjects using the new gum have quit smoking. So the problem here is that they only chose 10 adults. So there is not enough replication at all. So it could have just been that those 5 people maybe were really ready to quit smoking and they would have done it anyway without the gum, right? So it's not enough. 10 people are not enough. So we need more replication there. Here, the company identifies 1,000 adults. Okay, so that's better. We have lots of replication here, 1,000 people who are heavy smokers. The subjects are divided into blocks according to gender. So they're going to use that block grouping. So they're going to group it as females, female, and male. So that's one block. Here's another block. Females are given the gum, and males are given the placebo. After 2 months, a significant number of females have quit smoking. All right, so the problem here is that the only ones who are given the gum are all female, right? That's not representative of the population. So what we should have done instead is taken the first female block, given some the gum and some the placebo, and then for the male group, did the same thing, give some males the gum and give some males the placebo. So that's what we should have done to make this better so that it is more representative of our population.